Okay, so block matrices. Block matrices can be a really useful tool in computation when you have large matrices that are very sparse, which is often the case, especially in processing some data with a large data set, as those matrices tend to be mostly zeros. So using this technique can sometimes simplify computation and reduce the number of operations you need to actually carry out your multiplication or your matrix addition. And I'll show you an example of that a little bit later. All right, so first of all, blocking matrices just literally means chunking the matrix out into smaller blocks. Like, for example, I could break this matrix up in this way, and then I've sort of chopped A into 4 smaller matrices. And the notation that we use for doing something like this is this. So we'll call this little matrix the 62011. We'll call it A11 because this is again rows by columns. We're just talking about blocks now. So this is the first block in the first row in the first column, and I should probably put air quotes around first row because I really mean row of blocks. And this is in the first row, second column, and this is the second row, first column, and second row, second column. And so here, right, A11 is this little tiny matrix C6201. And A12 is, let's see, first row, second chunk is 30, and so on, right? And I could block B up as well. If I choose to do it like this, then I would have 2 blocks, each of the same size. Or I could do it exactly the same way that I've done A. So I'd have 4 blocks that have these corresponding sizes. Now, when you're adding blocked matrices, the rules for adding matrices that are divided up into blocks are exactly the same as the rules for adding regular matrices that apply to the elements. You have to have the same size. So let me make up some new blocked matrices. So C11, C12, C21, C22. Think about adding this to a blocked matrix, D11, D12. Okay, so adding blocked matrices works very much the same way that just adding any old matrices works. So we just add component-wise. So the results of this adding these 2 matrices should give us C11 plus D11 and C12 plus D12 and so on. And the important thing to think about here is that in order for this sum of these blocks to exist, these blocked matrices, these sums of the blocks must exist. And we know we can only add 2 matrices if they are the same size. So these submatrices must have the same dimensions. So looking at these 2 matrices up here, if I look at the blocks that I've divided them up into, you can see that A11 has the same size as B11, and A12 has the same size as B12. So we could actually compute this sum by writing down the sum of the blocks. Right, and so on. And this here doesn't really save any computation time because, well, these matrices are not sparse, right? There's a lot of non-zero entries in them, but this is just to get the idea. Right, so that's how you add blocked matrices. The number of blocks has to be the same. The sizes of the corresponding blocks have to be the same in order to do addition. And there's a bunch of numerical examples of this in the text, so I'm not going to do a whole bunch of numerical examples for you now in this video because I kind of want to talk about multiplication, which is, as always, a little bit trickier. So let's say we have a couple of blocked out matrices, say F blocked into F, and I'll make E. Okay, so certainly we cannot add these, right? So F plus E does not exist because they don't have the same dimensions, right? This one is got dimensions 2 by 3, and this one has dimensions 3 by 1. So just from the get-go, we don't even need to compare the sizes of those submatrices because there's a different number of blocks. So the sum F plus E doesn't exist. F times E, though, might exist. So think about what you would do if these were just entries in a regular matrix. So we have dimension 2 by 3 and dimension 3 by 1. Those interior numbers, right, the number of columns in the first matrix and the number of block rows in the second matrix match. So our resulting matrix, right, should be a 2 by 1. And then this is again 2 by 1 of blocks. So we basically, right, we think of having 2 rows, 1 column. We've got these 2 blanks to fill in. The first blank we're going to fill in just, again, by taking this row, first column, to get the first row, first column entry. So this will be F11 times E11, and then just kind of pretending that they're vectors and taking the dot product. So plus F12, E12, and F13, E13. The other entry we need to fill out is the second row, first column. So second row, only column. And so we get F21, E11, plus F22, E22, plus F23, E13. Oops, that should be. Okay, and so when we look at this now, we see that inside this product of these blocks is a whole bunch of products of matrices. So in the case of multiplication, the dimensions of the blocks have to match up the same way multiplication does, and all of the products must exist. So these matrices, the interior parts now, we do have to worry about those being conformal, right? And so when all of this works out, we say the matrices are conformal for multiplication. Okay, so and again, there's a bunch of numerical examples in the textbook, so I'm not going to go through a bunch here. I did want to show one example, though, of how matrix multiplication can be well, we can save a lot of time by taking advantage of some of the internal structure of matrices if we know something about them by using blocks. Okay, so here's a couple of matrices for us to play around with. I've already made a note over here that, that this product that I want to compute of these two matrices does exist, and that's because the dimensions are 4 by 7 and 7 by 2, respectively, and the number of columns in the first matrix matches the number of rows in the second matrix, so you can kind of think of them canceling out. What we're left with is a 4 and a 2, and those tell us the dimensions of the product matrix. So we know that this exists, and we know its size. Now, I can see qualitatively looking at this matrix that there's a lot of zeros. It's not really enough zeros to be considered sparse matrix, but it's more zeros than we've had in some of the earlier examples. So I'll show you what I'm going to do. I'm going to partition this matrix into 6 submatrices. So 2 of them have dimensions 2 by 3, and the others are all 2 by 2s. And then I'm going to partition this matrix into 3 submatrices. Now, the way I've done this, it's made sure that these 2 matrices are conformal for multiplication. So let's check that out. The dimensions of these matrices in terms of blocks are, let's see, the first one, X, has 2 block rows and 3 block columns. So this is in blocks, right? The other one is in entries. And this one has 3 by 1 blocks. Now, again, because the number of columns of blocks in the first matrix matches the number of rows of blocks in the second matrix, those two matrices can be multiplied, provided their interior matrices can be multiplied, and the result is going to be a matrix that is 2 by 1 blocks. So let's see if we can compute the product of x and y and make use of some of these matrices, submatrices that are of special types. So let's see. I know that xy, the product xy as in terms of blocks is going to be 2 by 1. So I know that I'll have 2 rows and just 1 column. And let's write out what those are going to be. So it's going to be x11, y11 plus x12, y21 plus x13, y31 for the first entry. And the second entry is going to be, let's see, x21, y11 plus x21, oh sorry, 22, y21 plus x23, y31. Okay, so that looks like, we've got a lot of computation to do, but it's really not too bad because we're going to make a couple of observations. First observation we're going to make is that x11 is actually the zero matrix, the 2 by 3 matrix full of zeros. So anything that we multiply by x11 is just going to be completely annihilated. So that's this term right here. There's nothing to compute because we know x11 is the zero matrix. We also, if we take a careful look, we'll see that y21 is the 2 by 2 zero matrix. So anything we multiply y21 by is also going to be just 0. Right? So those terms go away. And a couple of other things that we can notice is that, let's see, x13 and x23 are both the identity matrix, the 2 by 2 identity matrix. And the identity matrix for matrices is sort of like how 1 is for numbers, right? You can multiply any number by 1 and it won't change the number. You can multiply any matrix by an identity matrix that's the right size and you won't change the matrix. So that means that multiplying x13 by y31, it's just like multiplying y by 1. So we don't actually need to do any calculation, right? We're just, and the same with x23 because that's also an identity matrix. So really what we have left when we're carrying out this matrix multiplication is just y31 and x21, y11 plus y31. And this is great, right? Because this cuts the number of computations down a lot. In a video coming up, we're going to talk a little bit about computational time complexity of matrix multiplication. And in the most general case, matrix multiplication is big O of n cubed, where n is the largest dimension. So in the case of these matrices, 7 is the largest dimension that shows up. So multiplying without using the blocks and just doing the straight ahead algorithm for multiplying, x times y would cost around 7 cubed operations. And if you compare that to what we got down to down here, there's no operations in this first part. This is x21. x11 is a 2 by 3 and y11 is a 3 by 2. So this, using these blocks, got us down to around, like big O of 3 cubed. So 7 cubed is 343. 9 cubed is, of course, 27. So you can see that this is a huge savings. Now, these are tiny matrices compared to what you might find in any kind of actual real-life application. And these are not sparse. In real life, you might end up with a matrix that, has 99% of it is zeros. So if you can take advantage of the sparsity by using blocks like this, you can really cut down your computation time. So this is one way you can use blocks to multiply matrices and save yourself some trouble.